complex plane, compared to the R2 plane. In the complex plane, we've got an imaginary axis. So this goes up in multiples of I, right? This vertical axis, and this is the real axis. So real axis, imaginary axis. Where here a point will say z equals 3, 1 means so 3 plus 1 times I, or just I. And we plot that by saying, let's go over 3 on the real axis and up 1 on the imaginary axis, and we have a point here. And it's sort of, we actually visualize this point V almost as being a vector pointing from the origin 0, 0 to the point 3, 1. Where in R2, we would just simply say x, all these different variables, say A is the point 3, 1, just means going along the x-axis. We'd go 3 over on the x-axis, 1 up on the y-axis, and we have this point. We also think of, we have some other familiar terminology like the vector A, which represents, we'll say it represents the vector pointing from the origin to the point A. So we have a similar vector here. Oops. Similar vector here. Okay, so this analogy here, this actually is something in algebra is called an isomorphism. You don't need to worry about that, but this analogy here helps us do a lot of things because all the familiar operations that we did with vectors in R2 and in R3 and R4 and R5, so on and so forth, we can do to Z here. So as an example, if we have Z is equal to x plus iy and w is equal to a plus ib, well, z plus w is natural, right? It's just, so if we had these in coordinate form, this would be xy, this would be ab. Well, that means that in coordinate form, z plus w would be x plus a, y plus b, and it turns out this actually is true. So by definition, z plus w written this way is the same as x plus a plus I times y plus b, right? So visually what this would look like, if we're in the complex plane, and say we have a point, this is z, and this is w, right? I should actually be using some different colors. So we'll say this is z, and w will be green. Why not? W is this. Well, z plus w just represents the same thing that vector addition would do. So it represents the vector where if you were to translate w up here, right, just the vector going from the tail of z to the tip of w. This vector here would be z plus w. Right, these geometric vector addition and vector subtraction properties of complex numbers aren't going to be extremely important in FP2, but it's it's nice to visualize the comparisons between C and R2 because it helps convince ourselves that there's a lot of familiar formulas that we can use, so on and so forth. So now for some quick definitions that we're going to use over and over again in this monstrous section. So first one, real part of Z. Probably have seen this before. The real part of Z is just what would be X. So actually, you know what? I'm going to be more pedantic here. So Z equal to X plus IY. If we have a number, complex number, Z equal to X plus IY, well then the real part of Z is just equal to X, and the imaginary part, what we call the imaginary part of Z, is equal to Y. And keep in mind here that both the real part of Z and the imaginary part of Z are real numbers. So I mean, even though we call this the imaginary part, it's a real number, right? So another thing that we're going to define, modulus of Z or length of z, different ways of calling it. So we're going to call it the modulus. So the modulus of z is going to be defined as the Pythagorean length. So if we were to look at this in the plane, if we have just some random point z, we're just going to say is xy. Well, this height here, so this is our triangle we're using. This length here is x, and this height here is iy technically. We're going to just actually consider the real length. So here this would be x squared plus y squared. This is just basic Pythagorean theorem being applied to this number. So the reason that I goes away is because we want, I don't want to go too in depth in it, but it's something we end up actually defining the length as being z times the conjugate of z, which we're going to talk about later, but times the conjugate, the square root of z times z conjugate, and z conjugate is just all the imaginary parts of z going to minus the imaginary part of z. Sort of like the way that we define a square root conjugate. So if you had 1 plus square root 2, for example, the conjugate would be 1 minus square root 2, so on and so forth. Won't get into that right now. We can actually just take this as a definition for FP2. We don't really need to know all the intricate reasons why we define this as being the modulus. So let's just call it a definition for right now. Right? And often in FP2 you'll see this notated as an R, denoted by R. And there's a reason for this. There's a very, very particular reason for it, which we'll get into in just a second. So, one really amazing result, one really amazing tool of complex numbers is the fact that it can be put into what is called modulus argument form. So modulus argument form looks like this. So if we have a complex number z, which is the same complex number up here, this x plus iy, we can actually write this as modulus of z times cosine of the argument of z plus I times the sine of the argument of z, where, remember, this is FP1 stuff. Close my brackets. Argument of z is the angle here that z makes with the axis, the real axis. Right, so this is our argument. Right? So this is really sort of amazing. How could this be possible? Well, there's a long proof for it, but we're not going to get into it. It's just, actually, for this, basic common sense can tell you, right? So to go from here to here, well, all we have to do is, remember the length of this here is modulus of z. All we have to do is say, well, x is equal to the length here multiplied by the cosine of this argument, right? This is just basic trigonometry. So we here have x is equal to modulus of z cosine of argument, right? And the same thing can be said here. Well, forget the I for a second, because remember we're just going to pretend like that's it's a coordinate in R2. So the y here can actually be shown just basically trigonometrically as being modulus of z sine of argument. Right? Okay, so this is really convenient. For shorthand, we're going to say let theta equal argument of z. Then z can be written as modulus of z times cosine theta plus I sine of theta. Right, so let's do a basic example, because this is all very theory right now. Let's take the number cosine, or z equals 1 minus, you know what, I'm actually going to change this. So we are going to say, let's take 1/2 minus root 3 over 2 I, and we want to put this in the modulus argument form. So put into modulus argument form. So obviously what we need here, if we're trying to put this in modulus argument form, is the modulus and the argument. So let's do modulus first. Modulus is easiest. So by our definition, modulus is just the square root of the sum of the squares of the components. So here we have the square root of 1/2 squared, which is 1/4, plus root 3 over 2 squared, which is 3/4, which is equal to 1. Cool, nice and convenient. What about our argument? Well, here it's going to actually be useful to make a plot. So I'm going to say, in the complex plane, the number 1/2 root 3 minus root 3 over 2, I, is something that looks like this. So we go over 1/2 and down root 3 over 2. So we're in this quadrant down here. So how can we find this angle here? Well, this length here is 1/2. This length here is minus root 3 over 2. Right? So that means that this angle's tangent, so the tangent of that angle, so tan of theta, is just going to be equal to minus root 3 over 2 divided by 1/2, which is just minus root 3, right? Make sense? So what's the tangent inverse of minus root 3? We want to work in radians here. So the tangent inverse of minus root 3 is, I hope I'm making this, get this right, minus pi over 3. So it means we have an argument of minus pi over 3. So putting this in the modulus argument form, we have z equals our modulus, which is 1, times cosine of our argument, which is cosine of minus pi over 3. And then we'd have plus I sine of minus pi over 3. All right, so really quickly verify to yourself that if you were to plug this into a calculator, cosine of minus pi over 3 does in fact give you 1/2, and sine of minus pi over 3 does in fact give you minus root 3 over 2. Right, makes sense? Okay. So let's try a couple more things real quick. So if we have a complex number z1 and another complex number z2, so these are both complex numbers, we're going to just quickly prove to ourselves that the modulus of z1 times z2 is equal to the modulus of z1 times the modulus of z2. And this is obvious in real numbers, right? You have any number x, multiply it by any number x, you get, or sorry, any number y, you get xy. Well, the modulus of that is the same thing as the modulus of x times the modulus of y. It's not as obvious in complex numbers. So let's go ahead and prove this. We'd say let z1 equal x plus iy and z2 equal a plus ib. Well, this means that z1 times z2 is equal to, well, just x plus iy multiplied by a plus ib, where here we actually just multiply the way we multiply any two binomials, right? We just FOIL, expanding brackets. So we get ax plus ibx plus iay minus yb. Okay, so I'm going to rearrange this really quickly. I'm going to say this is ax minus, I really should be writing by. Keep it all in a nice order. Ax minus by, and we're going to say plus I bx plus ay. Right? So what's the modulus of this? Well, modulus is just the sum of the square root of the sum of the squares of the terms. So we have the square root of ax minus by quantity squared plus bx plus ay quantity squared. Right? We're going to leave it like this for right now. Because what we're going to do is we're going to start from the other side of the equation. We're going to try and get z1 modulus times z2 modulus equal to this. Let's see, bx, right, bx, ay. Yes, okay. Actually, you know what? I'm going to go ahead and expand mine as well. So if we were to expand all these terms, we get the square root a squared x squared minus 2axby plus b squared y squared. We get plus b squared x squared minus, plus 2axby plus a squared y squared. Right, so the 2axby's cancel. So we'd be left with just the square root of a squared x squared plus b squared y squared plus b squared x squared plus a squared y squared. So let's see. How can we make this look better? I'm going to continue writing over here. So we'd have, let's group the a squareds together. So we'd have a squared times, and here we have x squared plus y squared. Then we'd have b squared, again, x squared plus y squared. Okay, so we've got an x squared plus y squared in both of these, which means we can factor out the x squared plus y squared. So we get the square root of, in brackets, a squared plus b squared times, in brackets, x squared plus y squared. And since we've got two things that are multiplied together, we can separate them under a square root. We would separate the square root. So if you write this as square root of a squared plus b squared, you can probably see where this is going, times the square root of x squared plus y squared. Well, this is just the definition of the modulus of z2, I guess. z2 times the modulus of z1. Well, these are both real numbers, so we can separate them. We can switch the multiplication. This gives us modulus of z1, modulus of z2, which is exactly what we wanted. So we started off by calculating z1, z2, modulus of that whole thing, and we ended up getting that that's equal to the modulus of each one and multiplied together. So, kind of a hairy proof, but it's nothing too difficult about it. You're not responsible for the proof. I just wanted you to see where it came from. So, let's continue. A similar thing can be shown really quickly for z1 divided by z2 in a modulus. This can be separated into modulus of z1 divided by modulus of z2. That's another, I guess, relatively important result, although it's pretty obvious because you could just define, if you had the previous result, you could just define z2 to be, or some other z to the power of -1. You just had the multiplication. So nothing too weird here. What is interesting, though, is sort of a simple case of de Moivre's theorem, and we'll get to de Moivre's theorem in a second. So if we have any two complex numbers, so z1, where we're going to say the argument of z1 is equal to theta 1, and we have z2, where the argument of z2 is equal to theta 2, well, actually, it can be shown, and this is a really strange result, that the argument of z1 times z2 is equal to theta 1 plus theta 2. And actually, even furthermore, the argument of z1 divided by z2 is equal to theta 1 minus theta 2. Now, I'm going to show you the first one. I'm going to show you this one here. I'm going to show you this thing. Because this other one here is longer, and it's the exact same concepts as this one, but it's longer, so there's no reason to do it. If you want to do it on your own, you're more than welcome to. I think it actually might also be in your book. but it's not 100% necessary to learn it either. Just know that it's true. And you will know that it's true once you get towards the middle of this chapter because you'll be using it left and right. So how can we see that this is true? Well, let's take two complex numbers, so z1, and we're going to write it in its modulus argument form. So we're going to say z1 is equal to modulus of z1, which I'm going to call r1, times cosine of theta 1 plus I times sine of theta 1. And we're going to say z2 is equal to r2 times cosine of theta 2 plus I sine of theta 2. So just so we don't get confused here, I'll say modulus z1 equal to r1, modulus of z2 equal to r2. Okay, what happens if we take z1 and we multiply it by z2? So z1 times z2 gives us, well, r1 cosine theta 1 plus I sine of theta 1. It's not going to all fit here. Times r2 cosine of theta 2 plus I sine theta 2. Okay, well, let's expand this. We would get, coming up front, r1 times r2, and then we have to expand all these brackets, so we get cosine theta 1 times cosine of theta 2, right? And then we get cosine theta 1 plus I times cosine of theta 1 times sine of theta 2. Right? And then on the bottom here, we get, I'm going to do the imaginary part. So the real part first, I'm going to do this term times this term. We get minus sine of theta 1, sine of theta 2. And then we get, our last term would be sine of theta 1, cosine of theta 1 times I. So plus I sine of theta 1, cosine of theta 2. Okay. I've written it this way purposely because the real components go here and the imaginary components are here. So, how does this help us? Well, let's continue simplifying. So we have r1, r2 up front. This cosine theta 1 times cosine of theta 2 minus sine of theta 1, sine of theta 2 is the definition of the expansion for cosine of two angles being added. So if we had cosine of theta 1 plus theta 2, this is cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. Right, which means we could take these two terms and write them as just brackets cosine theta 1 plus theta 2. Right? Well, similar thing can be done here. So we have an expansion for sine, which is that sine of theta 1 plus theta 2 plus not times is equal to, so sine of theta 1 cosine of theta 2. I'm going to leave off the brackets just so it'll fit, plus sine of theta 2 cosine of theta 1. Actually, it fit with brackets. Okay, well, that's exactly what we have here. The only difference is we have an I in front of it. So all we have to do is take the I out, and we're left with sine theta 1 plus theta 2. Okay, here I claim that we've actually already proven it. We've actually proven two things in one. We've proven our previous result, which is that the moduluses multiply, or the moduli multiply, right? Because we had, if we were to take modulus of this whole thing, the modulus of this thing is just 1. And we have r1, r2, which are both real numbers. So that's, again, proven. But we've also proven now that this is another complex number. We'll say this is another complex number, w, with argument of w, argument of w, equal to theta 1 plus theta 2, right? And modulus of w equal to R1, R2. So this is actually sort of a multi-proof. We've proven, because remember that, I'll say, but W is equal to Z1 times Z2. So what we've done here is we've proven that the moduluses multiply and that the angles add. We did the proof for the moduluses multiplying the explicit way by writing it in terms of its components, which is also a good thing to see. But here's a more powerful version of it. Here we get two really nice results. Okay, so we're going to do one more thing, and then we're going to call it, because we've already done quite a bit. So the last thing is, and your book doesn't do this, it's not 100% necessary, but I'm going to do it because I like the proof, and it's kind of important for what you do later on. Actually, no, you know what? I'm not going to do the proof right now. I might do it in the next one, but the proof is fairly simple. So there's a really nice theorem called Euler's theorem. Euler's theorem states that if you have an exponent, or sorry, an exponential, so this is e, our regular e, our base of natural log, e to the power of I theta is equal to cosine of theta plus I times sine of theta. So this is an incredibly useful tool because, as you can imagine, if we had z equal to, I don't know, let's say 1 plus 3i, and we wanted to find out what z to the power of 1000 is, well, clearly taking 1 plus 3i to the power of 1000 and doing the binomial expansions and expanding this, you'd get a lot of terms that it would take you a ridiculous amount of time to do. It's not a feasible thing to do. But if we were able to put it in this format, then it'd be simple, right? Because taking an exponent of an exponent is just the same as multiplying the exponents, right? So this theorem is actually really useful, especially in circuitry and in physics and things like that, but also just in regular computational math. And because of it, we can say that an alternate version of the modulus argument formula is that z can be written as r times e to the power of I theta, where r is just the modulus of z, and theta is just the argument of z. All right, so let's do the same example that we did earlier. We had z equal to 1/2 minus root 3 over 2i, and we found out that the argument here, argument of z, was minus pi over 3, and the modulus was 1. So we would have now that z can be written in modulus argument form the way we had it before, and also it can be written as 1 times e to the power of minus I times pi over 3, right? Which is just e to the minus I pi over 3. So why is this nice? Well, if we wanted to find out what z to the power of 300 was, then how could we do it? Well, this would just be e to the power of minus I pi over 3 to the power of 300, which is e to the power of, so let's see, minus 100 I pi, right? All I've done here is I've said, let's take 300, let's multiply by pi over 3, I pi over 3, and you get this, 100 I pi times minus 1. So, what if I wanted to see what this was in component form? Well, I could decompose this now into modulus argument form, right? The modulus argument form version of this, according to this formula up here, is cosine of minus 100 pi plus I sine of minus 100 pi. So what's the cosine of minus 100 pi? Well, it's an even power of pi, it's an even multiple of pi, and for all even multiples of pi, cosine is equal to 1, right? So here we just have 1. And any power of, or any multiple of pi, if you take sine of that, it gives you 0. So here we get 1 plus 0, which is equal to 1. So clearly this is a lot easier, much easier than saying 1/2 minus root 3 over 2 I times 1/2 minus root 3 over 2 I times 1/2 minus root 3 over 2 I. Well, 300 times. That's what you have to do. But if you were actually to do that, if you were actually to multiply that 300 times and add up all the like terms, it would give you exactly 1. So this is a really, really useful tool. We've saved ourselves a lot of time doing this really, really, really basic stuff. We haven't really even done that many things. Our example starts here. Our example starts here and ends here, right? Whereas if we were to do it this way, we wouldn't be able to fit it on probably even 20 pages. It would take so long. So I'm hesitant to do any more. I'll go ahead and write down de Moivre's theorem. I'll write down de Moivre's theorem just because it's a nice thing to use, and because it's not that difficult to understand if we write it in terms of the exponentials. So we've seen now that z can be written as r e to the I theta, and can be written as r times cosine theta plus I times sine of theta. Well, de Moivre's theorem states that for any integer n, so any, actually, I think it even goes as far as to say any rational n. Yeah, I think it's any rational. So for any rational number n, and what I'll do is in the next video, I'll prove it just for positive integers. So for any rational number n, z to the power of n can be written as r to the power of n, e to the power of I n theta. Right, this one's sort of easy to see. It's just just using some basic exponent rules. Right. Well, this is the more powerful one, or the one that, it's not more powerful, but it's more shocking. Is that this can also be written as r to the power of n times cosine of n theta plus I sine of n theta. Right? So I'll do a really brief sketch of the proof. I wasn't going to do it, but I think for positive integers it's fairly easy to see. So we've got a formula that depends on n. So we'll say for positive integers, for n belonging to positive integers, or I'll just say natural numbers. We can prove this by induction. So we'll say for our base case, we have n equals 1. Well, clearly this is just Euler's theorem, right? So for n equals 1, we have z equals r times cosine of theta plus I sine of theta. Actually, we can even do this a little bit further. We can say for the natural numbers plus 0. And we could say for n equals 0, we just have 1 equals 1. So we have a good case, right? Because z to the power of 0 is the same thing as all this to the power of 0, and those both give us 1. So, sure, fair enough. Doesn't really matter. You can do it for 1 or for 0. Okay, now our induction hypothesis is going to be that we're going to assume this holds true for some value k. So assume true for some n equals k. Right, so we have assume that this is true for some fixed value k. Theta. And we want to show that it's true for the n equals k plus first case, right? Basic group by induction. So what is the k plus first case? Well, z to the power of k plus 1 is equal to all this stuff, right? So it's equal to r to the k times cosine k theta plus I sine of k theta times r times cosine theta plus I sine of theta, right? Because we can separate this as z to the k times z. Well, expanding all that and bringing the r's together, the r's are proven almost instantly. All right, we've got r to the k plus 1. R to the k times r is r to the k plus 1. And now we've got all these terms here that we've got to cross through and multiply. So I'm going to do what I did last time. I'm going to take the real values, and I'm going to group them together. I'm going to take the imaginary values, and I'm going to group them together. So the first set of real values that we get is cosine times cosine. So cosine k theta, cosine of theta. Next set of real values that we get is just multiply these two as well. So we get minus sine of k theta, sine of theta. And then our imaginary terms are going to be sine theta, I sine of k theta, cosine theta. So I sine k theta, cosine theta. And then our second imaginary term is going to be this term right here. So plus I cosine k theta, sine of theta. All right. So this is what our z to the k plus 1 is. Well, this is pretty clear. We've already done this exact same thing, right? This here is just the expansion for cosine of k theta plus theta. All right, so here we've got r to the k plus 1. Inside, we could write this entire expression here as cosine of k theta plus theta. And we're going to write this entire expression here as, well, I sine of k theta plus theta. Well, all we've got to do is factor a theta out, factorize a theta out from each one of these terms inside of our trig functions, and we end up with r to the k plus 1 cosine of theta times k plus 1 plus I sine of theta times k plus 1, close brackets, close brackets, brackets. Well, this is exactly what we wanted, right? Because we wanted it to look like this, but with a k plus 1 replacing the k with the k plus 1. So this is exactly what we wanted. So here you'd write our conclusion, which I'm not going to include because you should be relatively experienced with the conclusions right now. But this is proven, and keep in mind we've only proven it for negative integers. I'm sorry, for positive integers. We have not proven it for negative integers. The proof for negative integers is almost identical, but you have to make a quick little change of variables in the beginning, and everything else works exactly the same. Okay, so I think that's going to be it for this video.